Hi class, this is Peter Smallage. I'm recording this third lecture of the course Forest Management and Maple Syrup Production in the year 2014 for you to watch at your viewing pleasure and leisure. This lecture is on how forests grow. It's basically a lecture about forest succession. So let's first define what forest growth is. Forest growth might also be described as the development of the forest, or forest development, or forest succession. Philip Grime, who we'll learn more about in just a few minutes, has defined this as a progressive, so that means through time, a progressive alteration or change in the structure and species composition of the vegetation. When we think about structure, we think about what the forest or the plant community looks like. Are they all big trees, all little trees? We saw some structural differences in lab last week. And species composition would be a description of the variety of species that are present. So a change in what the forest looks like in the mixture of species. The relevance of this to woodlot management is quite significant because all of our forests change. There's many landowners are hopeful that their forest would remain the same, or some section of their forest would remain the same as always, but as you can see in these pictures where we have a stone wall or a couple of different stone walls embedded in the forest, these were areas that were once pasture and are now forest, and these continue to be forests that change. Our objectives for today then are to be able to describe and understand the environmental, land use, and management factors that influence forest growth. I want you to be able to compare and contrast the conceptual models of succession, forest succession. These are models that incorporate tree life history traits into these models and be able to incorporate those tree life history traits. And we'll discuss a few of those. I want you to be able to list and describe how various management options are useful during each stage of forest succession. So this is essentially a 1 hour lecture on ecology, what you may have had for a full semester, but we're going to break it down and look intensely as to how forest succession relates to forest management. And this would have application to sugar bush management or maple syrup production in the sense that those maple sugar bushes will also change through time. So why should you care? And this is always a good question to ask and to answer. You could frame this maybe a little differently, thinking about how does this relate to what we're interested in this semester. And what I will argue is that if you understand what's causing the changes in the forest, then you can anticipate those changes. So you can anticipate the timing of those changes, how those changes are going to affect the mixture of species, what the forest looks like, the structure, and then you can use that information to optimize objectives that you might have that would relate to economics or wildlife or aesthetics or forest health. So this is a powerful tool for us to use to make decisions. It can save time and money, and it can focus our efforts. So here's a kind of a depiction of some of a lot of the New York landscape and the northeastern landscape. In the upper corner, you can see where, upper left-hand corner, you can see where the forest was an old-growth forest that subsequently changed to a cutover forest. You can see the two men in the lower right-hand corner of that lower left-hand box. And then moving to the upper right, you can see those cutover lands became farm fields, and eventually, as you move to the lower right, you can see that those farm fields eventually reverted back to forest. This is the natural condition of the soils of New York and the Northeast. Okay, here's another example of forest succession. We can start in the upper left-hand corner. This was a forest that was clear cut, and this is in northwestern Pennsylvania near Kane, Pennsylvania. It's on what's now Forest Service research forest lands, and it was what's called a chemical wood cut, so it was a full and thorough clear cut. This is not different really from what you saw at the Arnott Forest last Thursday where we looked at that strip clear cut. So it's a different spatial configuration, but the same type of management activity where all stems were cut. As you move to the upper right, so moving clockwise, you can see a young forest that has regrown. That looks a lot like what we saw at the Arnott Forest. Shifting to the lower left, you see what would be called a pole-size stand. And as you're looking at these pictures, think about the changes that we're seeing in the forest, the change in the sizes of the trees and changes in the strata where vegetation occurs. So the strata in the upper left-hand corner is very low. The strata in the upper right-hand corner is still relatively low. It's less than 20 feet. In the lower left-hand corner, we can see that the lower strata has disappeared, and we now have an upper canopy that has developed. You can see in the lower right-hand corner of that. Down here, you can see a forked tree. In that same forked tree, that same forked tree is located over here as well. So, anyway, I'm not doing very good with my pointer, but you get the idea. Forests change through time, and we need to be thinking about how those changes will be reflected. So the succession of a forest is really the struggle for survival and for dominance. And I've listed 8 different factors that influence that struggle and who wins and who loses. It includes things like the climate, the disturbance patterns, soil, seed sources, soil conditions, what wildlife are there particularly. And you can think about at different stages in the life of this forest. Wildlife might be important as pollinators, such as butterflies. Wildlife might be important as dispersers of seeds, both dispersal of desirable and undesirable seed sources. And then wildlife such as deer might be relevant as browsers. Each tree species has particular characteristics that will make it more or less successful under the suite of conditions that are present. And then there are also pathogens, and there's also just random luck. Sometimes you have bad luck, sometimes you have good luck. As we consider these different factors, think about how a change in any one of these factors on a particular point of ground would influence or redirect the trajectory of succession. So if we look in that picture on the upper left-hand corner, and that was in northwestern Pennsylvania, how would this change? How would that trajectory be different, perhaps, if the same? I mean, it would be a different species mixture if we were in southern Georgia or central Idaho. But think about how those different climatic patterns might affect the rate of change and the type of change. So one way we can think about how species arrange themselves, which species we see as dominant and which species maybe don't even exist, is based on called the CSR model, or the plant succession model triangle of J. Philip Grime. This is from his book Plant Strategies, and he's basically arguing that plants have a strategy, and that's not in a deliberative sort of use of the word strategy, but these are characteristics of a species that allow it to succeed in some circumstances and to fail in other circumstances. There are 3 primary strategies that a species will have, and this is, if you're familiar with the soils triangle, this reflects a common pattern of the soils triangle. So one side would be a competitive leg, another side would be stress tolerant, and a third side would be a ruderal or a disturbance leg. So you can imagine a species where the red dot is located as having very strong competitive abilities, but relatively weak in its ability to tolerate disturbances. A species of that, for example, might be sugar maple or white ash. So these are species that are relatively competitive. They also would be fairly tolerant of stress. You can see that it's low on the stress curve, and also, or high on the stress curve and low on the disturbance curve. A stress-tolerant species is a species that's efficient at gathering resources when they're limited. So you think about a stressful environment would be species that grow on sand dunes or on gravel, outwash soils. And then ruderal species are species that have the ability to arrive quickly and then to be dominant once they arrive. So these are species that have good mechanisms of seed distribution. So let's profile two of these species and think about them in the context of stress, in the context of competition for sunlight, and in the context of response to disturbance. We have northern red oak that tends to be relatively intolerant of shade. It has a high it's highly preferred by deer, so it has a high browse preference. It does not have a particularly strong ability to disperse or retain its seeds. The seeds don't start being produced until the trees are about 16 inches in diameter and the trees are about 50 years of age. It does have the ability to stump sprout. It will not root sprout. Contrast that to striped maple. This is a species that's tolerant of shade. It's not preferentially browsed. It probably does not form a seed bank. It does produce seed on a very frequent interval and will form a seedling bank. So the seedlings will form and then remain dormant in the understory, or stagnant. They'll not dormant. So they'll continue to be alive as seedlings, making no appreciable height growth, and then just kind of hang out in the understory, waiting, if you will, for a canopy gap to open. The seeds begin production, of the trees begin production of seed at about 7 years of age and 2 inches, and the species has the ability to change sexes in response to disturbance. So if you stress this tree in some fashion, it can change from a male to a female and produce a significant number of seeds. It will stump sprout, it will not root sucker. So if we think about this relative to the competitors, the stress tolerators, and the disturbance species, we can imagine that these two species would find a different location on that triangle. We can also represent those three different characteristics on a two-dimensional graph. On this two-dimensional graph, and what we're trying to do is think about where these different strategies would be most pronounced, where they would be most evident. So if we look on the x-axis, the time since disturbance, and on the y-axis, environmental stress, we can see that if we have a short time since disturbance, so that area closest to the 0 line on the x-axis, the ruderal species or the disturbance-prone species would be most likely to dominate there. As we increase the time since disturbance, those ruderal species will disappear. We saw that, for example, at the Arnott Forest when we were in the oak, and as we were walking up that hill, and we saw beech in the understory, and the overstory was red oak and big-tooth aspen, and the big-tooth aspen were dying. This was a forest we talked about being on the order of 100 or so years of age. The big-tooth aspen had become established, but it's a long time. It's 100 years since disturbance, so those disturbance favored or ruderal species are starting to die out. And as the environmental stress increases, you're going to shift from species that have competitive strategies to species that have stress-tolerant strategies. So we can join that plant strategy model of Philip Grimes with two, I'll say, historic models of species of forest succession. So that one of the point here is that the Grimes model is not an alternative to these two, but rather explains the mechanisms by which we might see these two strategies play out. We have the original model of of succession that was developed by Frederick Clements. This is called relay floristics, and it was challenged by Henry Gleason with the initial floristics model. So let's look at both of these, and both of these have a place. In Frederick Clements's relay floristics model, we see this depicted graphically, where you have three different tree species, A, B, and C, and the zero line would be the starting point after some large-scale disturbance or even a small-scale disturbance, and you have these species establish. The point is that the first species to arrive when there's an availability of resources will control the site and will exclude other species. As time progresses, the original species A, B, C will eventually die, and those will be replaced by species D, E, and F. So you can see the thickness of the bar is the extent of dominance of that species. So these species, hypothetical species, are equally dominant within this forest community. These later species can survive because the early species modified the site, and that's a key element. Two key elements here. One, the initial species modify the site. Second key element, maybe there's more than two. The second key element is that they exclude other species by their presence. The third key element is that they modify the site. Their presence modifies the site to allow for the arrival and success of subsequent species. Now, in the relay floristic succession model, species A, B, and C may not be all tree species. There might be some herbaceous or other kinds of species that are present. But the basic principle is it's a relay. You hand off dominance of the site from one suite of species to another suite of species. So the summary here, early species dominate the site until they die. Those early species, and each group of species will modify the site in such a way that it's more favorable for species that arrive later. The early species and the site characteristics prevent later species from getting started. So this is not common in our eastern forests. Where you might find this common is in particularly environmentally harsh areas. So if you had a sandbar or you had an exposed rock face on a mountain, these are environmentally harsh sites. There are very few species that can survive in those, and those species do change the nature of that area as they live and as they die. The alternative model, this was Henry Gleason's model, is called initial floristics. And his argument is that all of the species arrive essentially at the same time. Here we see species A, B, C, D, E, and F. And at the starting point, they are all present. Not all of them are dominant. So at the early point, species A, B, and C are dominant. Species D, E, and F are present, but have not expressed their dominance. So all the species arrive at the initial starting point. The species that express dominance early are not likely to be as long-lived as the species that express dominance later. The key features here, all these species arrive about the same time. The fast-growing species dominate, but they don't exclude other species. And this is the pattern that we'll typically see in our eastern forests. And if we were to have done a thorough inventory of the clear-cut, we would have seen early successional species, the clear-cut we visited at the Arnott Forest, we would have seen early successional species and later successional species. And the species that are present there are the species that will remain present. There are not going to be new species in any significant way dominating the site. You may get an occasional species that comes in, but they're not going to dominate the site based on this model. So we look at this and we see that same basic pattern. In the upper left-hand corner, the chemical wood clear-cut from Kane, Pennsylvania. In the upper right-hand corner, that early successional forest. That forest has the full mixture of species that's going to occur at the later successional in the lower left-hand corner, and then in the mature forest in the lower right-hand corner. These stages of forest development have been named, and we just looked at those 4 different stages. These 4 stages are going to be important because they're going to dictate the types of management activities that would be economically feasible as well as logistically prudent. The first, and we'll look at each of these in detail, but let me just describe them as the stand initiation stage, the stem exclusion stage, the understory reinitiation stage, and then the old growth or mature forest stage. And you can imagine that these might be interrupted. As you see in the lower diagram, you have stand initiation, stem exclusion, understory reinitiation, so that's the same as above. Then there's some kind of a disturbance. It might be a windstorm or a clear cut, and then you accelerate succession by pulling species that are already existing in the understory and bringing them up into the overstory. So this graphical depiction has real application for us because we can think about the forest that we walk in, and they'll oftentimes have 2 different strata, an overstory strata and an understory strata. If we remove the overstory strata by whatever process, natural or anthropogenic, the understory is what is going to dominate that forest. But let's look at the classic model. Has 4 stages. Here they are again: stand establishment, stem exclusion, stand reinitiation, and steady state. This is what's described in one of the readings by Bob Peet and Norm Christensen, and also in Chad Oliver's bulletin that was developed about a year later. And so this is a pattern that's seen in forests throughout the United States, whether it's the Northeast or the Southeast or the Northwest. This is a fairly common pattern. The numbers that I'm providing in this chart would be appropriate for a northeastern forest. And there's always going to be a range because there are changes in the environment that would dictate how rapidly one stage is completed and the next stage is entered. So you can see those durations. Typically the duration is on the order of 20 to 50 years, and the changes in the number of stems is often 1/10 as we move forward from one stage to the next stage. We can look at this very simple image where we have a forest at its starting point and it moves through a trajectory. Now succession doesn't happen in a trajectory as we think of a vector having trajectory, but the intent here is to illustrate that it has a direction that it's moving, that there's a predictability to where it's going to end up, and that there's some known number of years over which that succession will happen before it reaches its endpoint. And the endpoint may be a terminal endpoint or a milestone endpoint. And we can think about how management influences that. So without management, we have the arrow going to the upper left, the black arrow, but when we add management to succession, we have the potential to guide, accelerate, slow down, or redirect how that succession happens. So the red arrow suggests that we can change the duration of succession, in this case shortening it with management, and we can move it towards a different endpoint. This illustrates a fairly radical different endpoint that in some circumstances is possible. It's typically not that dramatic of a change. Let's look now at the characteristics of these 4 different stages of forest development. The establishment stage, also called the stand initiation stage, is characterized by having abundant resources. So there's been some disturbance, a windstorm, an ice storm, a clear cut, and there's an abundance of soil resources, and particularly an abundance of sunlight. Plants will become established by either seeds, so sexual or asexual reproduction using suckers, root suckers, or stem suckers. The growth of these plants tends to be very rapid. That's because of the abundance of resources, but would also be that growth is going to depend, of course, on the soil conditions and a little bit on climate, so moisture, soil fertility. The duration of this phase or stage of stand initiation depends upon the stocking level, so how well stocked it is, the fertility of the soil, and the presence of pathogens and pests. So if you have conditions that are stressful, so low soil fertility, high incidence of pathogens, high incidence of pests, including deer as browsers, you can prolong the duration of this. And you can I think it's rather intuitive that when you know that the phase ends when the canopy closes, anything that stalls canopy closure, such as low soil fertility or heavy browsing by deer, will stall the closure of this particular phase. The management that we should be thinking about during this establishment stage is based upon presuming that there are going to be many thousands of stems per acre. So this becomes a circumstance where we're not able to really manipulate individual stems, but we might be thinking about doing some broadcast rather than selective manipulations, if that's desirable. If there are grasses and ferns and beech that are dominant before the disturbance, these can, if you remember that picture we showed just a few minutes ago, that the interrupted succession, those species can dominate, and they can essentially redirect succession such that these grasses, ferns, and beech are now the dominant forest community. From a management perspective, we want to monitor for the presence of species that are desirable, for the abundance of those species, so that's the stocking. Remember, we talked about basal area and stocking. So basically making sure that if we're trying to regenerate a particular suite of species, that those species are present. We want to be able to control the impacts of deer, and this is also a unique habitat for some wildlife species. There are some birds that are restricted to the niche that's provided by the early successional or establishment stage. The next stage is the self-thinning stage. This begins as the crown closes, so you can imagine this is a point of very intense competition. Some species will die. Certainly some stems will die. Those species that have a short lifespan and those species that are not competitive for the resources, or those individuals, will be the ones that will die. So there's going to, obviously within a particular species, whether it's aspen or sugar maple, there are going to be some individual stems that, because of their genetics or because of the soil conditions where they're living, are going to not be competitive for those resources. The number of stems per acre has maximized in the previous stage, in the stand establishment stage, and the number of stems per acre will decline. The faster growing species are often those that will die sooner. It's just the nature of their strategy. This particular phase ends when the species start to vertically stratify, so some species will be growing taller, some species won't grow as tall, some stems will die. This will allow for sunlight to penetrate to the forest floor and begin what we call the stand reinitiation stage. The management activities that we would undertake during the self-thinning stage correspond to the fact that there are typically going to be many fewer stems per acre than in the stand establishment stage. We're going to be down to maybe hundreds of stems per acre. These stems are going to be going through a process where the lower branches are dying back, so they're self-pruning. The stems are elongating as the trees get taller. Of course, they grow taller from the top of the tree. And this effectively raises the height of the canopy. So the base of the canopy is going to be getting further from the ground. It certainly is possible to go in at this point and thin, where you remove some trees so that you favor the growth of other trees, but it's going to be economically premature until the trees are probably at least 4 to 6 inches in diameter at breast height, or DBH. Even then, it's going to be a pre-commercial activity. The question is whether you can carry that cost forward until you're able to acquire some return on your investment. The, the exception to this is for sugar bushes, where you can be thinking about starting to collect sap from trees once they're 10 inches in diameter. So if you're doing a thinning at 5 or 6 or 7 inches, when the stand is an average diameter of 5, 6, or 7 inches, you're only a couple inches away from being able to acquire, starting to acquire some economic return. This is not going to be, thinning is not feasible though if your primary objective is for timber production. The third stage is a transition stage, which we'll refer to as the understory reinitiation stage. Some species are going to disappear completely. Certainly the early successional species were down to fewer stems per acre, maybe in the few hundred per acre. The faster growing species have mostly died, and what characterizes this stage is the development of a more complicated or diverse vertical structure. You can see that illustrated in the picture where we have, this is illustrating two different species and two different height classes. But the complexity of that vertical structure would depend upon the species mixture and the soil conditions. What allows for the lower strata to develop are that some species by their nature are going to be growing taller, and at the same time some stems are going to be dying out, so you have the opportunity for sunlight to be penetrating through the upper canopy and providing energy at the ground level where seedlings can become established. This is a chance for deer now who may be able to inhibit some regeneration or anything else that would have an effect at the ground layer. The phase ends when the vertical structure is well developed and we move into the steady state or mature phase. The types of management activities that we would want to undertake during the transition or stand reinitiation stage are several. And this is really when we can start thinking about having some commercial benefit from management activities, particularly thinning. The average stand diameter is probably going to be in the 8 to 12 inches, and so there's certainly the potential for the production of firewood. There may be some potential for the production of low quality saw logs, small diameter saw logs. We're going to expect to see some seedlings developing, and we may also see some undesirable plant species developing, beech or striped maple or some of the invasive non-native shrubs like multiflora rose or bush honeysuckle or European buckthorn, as those low light levels penetrate into the forest floor. There's a potential to think about harvesting the faster growing trees. These are going to be the biggest, largest diameter trees in the stand, but this would constitute what would be known as high grading, taking the highest grade or the highest value and leaving the lower value trees behind. Now there might be a variant of this. You can imagine you reflect back on the stand we visited during lab, and it was a mixture of oak and aspen, and the aspen were starting to die. It's conceivable that you could go in and start to cut the aspen if you had a market for it, and if you had somebody that had very good skills at felling trees, such that you're not damaging your more desirable and more valuable red oak. So that would be effectively a salvage activity where you're trying to salvage the value of that big-tooth aspen before it dies. There's not a lot of value in big-tooth aspen, but if you have a portable bandsaw mill, it's the kind of wood that you can, those trees have a great deal of volume and it makes decent lumber. So the final stage is the steady state or the old growth stage. Here we have experienced the death of the medium-lived species. These create larger canopy gaps because they're larger, taller trees, and we're forming multiple layers. The early successional species have all disappeared unless there has been some secondary large-scale disturbance that's overlaid on top of this four-part developmental sequence. Shade-tolerant species tend to dominate in the understory. This could be both desirable or undesirable shade-tolerant species. And we have the potential that deer and fern and beech and other species are going to be present in sufficient number and abundance that they will inhibit our desired reproduction. The overstory trees will all have the same age, but will have different diameters reflecting variation in growth. Management here can be fully commercial, the opportunity to thin. Remember, thinning is the process where we're trying to influence the characteristics of the current forest. We're not trying to regenerate the forest. So we're trying to concentrate growth on those best trees, and those best trees will eventually be used for the production of seed. It's important to be alert to the presence of deer and interfering species. Although regeneration may not be a near-term objective or a near-term activity, regeneration is a process that proceeds over 10 to 15 or 20 years, and the regeneration process in a managed forest would be initiated during this phase. As you're thinning, you want to be cautious to make sure that you retain all of your options in the sense of species diversity, particularly for those species that you want to retain. It would be imprudent to try to eliminate a particular species. Some species will naturally disappear, for example, aspen or paper birch. But those are species that are typically common enough on the landscape, and as we recall back to the ruderal species, have a mechanism where they have effective distribution of their seeds. Even if they're missing from a forest, if we create the right conditions, those species will be present and can establish. So as management activities are occurring in the steady state or the old growth phase, we need to be very conscious to what we're leaving behind because that is our legacy. So I'd like you, just as I'll say as a thought experiment, this is not anything you're going to turn in, but draw a curve, use 4 different graphs, so an XY axis, and show the number of stems on the y-axis and the diameter range for each of the 4 different developmental stages. So we'll do the first one here for, I'll do it on the screen for, this will be rough, but that's okay. So there's our XY axis, and the stand initiation is going to have, and down here we have diameter, all right, and then on the y-axis we have the number of stems. This is going to take some time. All right, so there's number of stems, and then if we think about what the diameter is going to be for the stand initiation, the average diameter is going to be very small, and the number of stems is going to be very large. And think about how the range of variation that's going to occur in those small diameter early successional stems. There's going to be very little variation, so you're going to have the point is you're going to have a fairly tight curve, something like that. So as we think about that, and then we were to think, I'll give you the other end point, let's think about the mature forest, the steady state forest, and we're just thinking about the range of diameters for the main canopy, not for the species that have established. There are fewer stems per acre, but there are going to be more variability. Right? So here's our new graph, if it's going to show up. It's not showing up for me. Okay, so there's one line, Here's our second line. All right, these are obviously kind of rough, but now our graph is going to be, the average diameter is going to be out here, something on the order of, you could say about anything 12, 14, 16, 18, 20 inches in diameter, and you're going to have a wide, flat, relatively flat, a low curve, so there's relatively few species per acre, few stems per acre, a lot of variability. So variability through time increases, number of stems through time decreases. And then we can look at all of these four different forest conditions. These are four different forests that have, three of them are at the Arnott Forest. The one in the lower left-hand corner is from the Catskills, and you can think about what are the conditions that are present here, what is likely to happen over the course of time for each of these different areas. And finally, some questions that you can think about while you're reading or perhaps rereading the papers that are part of the Lecture 3 series. Think about what season how season of last plowing, or think about the timing of a disturbance, how that might affect the dominant species. Think about why a stand would reach the stem exclusion stage, so pass through the stand establishment stage more quickly than other stands. And why do some stands never or only very slowly reach the stem exclusion stage? Can you consider if there are different ownership objectives that will influence the stage of management or the stage when management activities should start? So consider one management activity or one ownership objective versus a different ownership objective, and consider how those objectives would influence when we would initiate management. Ponder how soils affect the dominant species, and when sunlight is going to be limiting for the development of tree species after disturbance. Or is there a type of disturbance, or more aptly, a pre-disturbance stand structure where the conditions of that stand is going to result in a limit to the amount of sunlight that's available for the establishment of trees. Okay, so this concludes Lecture 3 on forest succession.